Today, I will talk about a sailing mobile robot named HanGrawler. We developed this robot and realized large payload and high-speed movement. At first, please watch this demonstration. HanGrawler moves under perforated metal ceiling plate with 40 kg load to hang from the ceiling like this movie. And using a turntable, two-dimensional movement is realized. Now, I will show the background on this research. Sailing mobile robots are suitable for parts transportation at production sites like this image. Using these robots, you can avoid interfere with worker and production facility spaces and realize various transport routes. Besides, existing sailing mobile robots require rail structures like this image. So, the robots have high-speed mobility and large payload. On the other hand, route adjustment requires rail replacement, so it is unsuitable for production lines which are changed frequently. For example, automobile assembly factories. So therefore, sealing robot with flexible route adjustment is desirable. In previous studies, two related robots are existed. HanGbot is a sealing mobile robot and has a mechanical hanging for perforated sealing plate. This mechanism realizes large payload but slow speed due to moving intermittently. The other, Rise Robot, is a wall climbing robot and has vacuum suction and crawler mechanism. This mechanism realizes high-speed movement, but heavy object transport is difficult. In order to get each advantages, it is important to combine mechanical hanging and crawler mechanism. This is a conceptual image of the sealing mobile robot, combining hanging mechanism and crawler mechanism. In this study, the hanging mechanism is locked onto and released from the sealing hole, and the crawler mechanism is continuously inserts hanging mechanisms. This combination is innovative, so we discussed 4 problems associated with the combination. In this study, we set the target payload to 50 kg and velocity to 0.1 meter per sec, derived from general conveying machines. About problem 1, hanging mechanism is switched between inserted into and locks onto a sealing hole and released and extracted from a sealing hole. This is a conceptual sketch of the HanGrawler. Hanging mechanisms are installed on a crawler mechanism, and they are moving along a driving direction. In this phase, the front hanging mechanism is in locking state, and the rear one is in releasing state. When large load is applied to hanging mechanisms, increase the state switching force, and it prevents high-speed movement. So, we installed support frame between the sealing and crawler mechanism. For this frame, load is applied to the hanging mechanisms just below the frame, and it realizes that locking, releasing hanging mechanism is free from the load. Next, we consider that how we can make insertion high speed. There are 2 hanging mechanism insertion methods. The first, vertical insertion, is inserting just below a sealing hole. This method has wide clearance but needs long insertion stroke. The other is in insertion along with the sprocket. This method is using crawler movement to insertion, so realizes short insertion stroke and contribute to high-speed movement. However, this method has narrow clearance, so it is necessary to avoid interference between the hanging mechanism and sealing hole. So next, we analyze the insertion trajectory of the hanging mechanism. To analyze the interference, we developed new design method for the hanging mechanism trajectory. In designing the hanging mechanism, the sealing lock part is important. In order to calculate the available region for sealing locking part, we considered the trajectory of the sealing hole edge from the hanging mechanism perspective. For example, I will calculate in this shape guide. The straight line is connected to the circular arc at an angle theta. The trajectories of the edges are as shown in this graph. When theta is 20 degrees, the trajectory is indicated as red line, and the red area is the available region. As theta changes to 10 degrees and 5 degrees, the trajectory and the region changes as well. In this way, we calculated the available region according to the guide shape, and it is found that a straight line and circular arc shape guide can secure a large region. About problem 3, to realize high-speed hanging mechanism state switching, we consider that single action switching between lock-release simplifies the switching mechanism. This is overview of hanging mechanism, and top view inserted into the sealing hole, and the image integrated with crawler. In this mechanism, push and pull action can switch the state. Push action performs to insert and lock. Pull action performs to release and extract. Next, I will show the movement. The hanging mechanism is inserted into a sealing hole using a push-pull mechanism. It pushes the hanging mechanism upwards and the locking part touches the sealing hole. It inserts the locking part while closing by receiving force from the sealing hole. When it inserts with a pushing stroke, the locking part opens via torsion spring and locks into the sealing hole. The locking part closes by pulling the release rod. Further pulling can extract it from the sealing hole. In this way, the hanging mechanism switches the states. About problem 4, to realize two-dimensional movement, direction change mechanism is necessary. So we considered to install a passive turntable guide on a steering and a rotating arm on a robot. This is a conceptual sketch of the direction change mechanism. A rotating arm is installed on a robot and rotates turntable via rotating arm. It is realized with small number of actuators and no electric equipment on sealing, and it realizes easy route adjustment. The right images is the overview of the turntable guide. Based on 4 programs, we combined each mechanism and developed HanGrawler. Crawler mechanism is driven along the crawler guide, and hanging mechanisms are installed on the crawler, and rotating arm is installed at the bottom of the crawler. In this section, I will talk about experiment of linear and turning movement. The experiment 1 purpose is to evaluate the performance of the combination with hanging and crawler mechanism. The target load is 50 kg and transport speed is 0.1 meter per sec. About the experiment conditions, load is 0 to 60 kg and movement distance is 400 mm. And wire encoder was used to measure the movement distance. Regarding the results, HanGrawler realized 0.1 meter per sec linear movement. This graph represents the movement distance and shows the movement was close to uniform speed. It appears that continuous movement was achieved. And this graph represents the average speed of each load. It shows that HanGrawler moved at 0.1 regardless of the load. So we considered the target load 50 kg and the target speed was achieved. Next experiment purpose is to evaluate the feasibility of the turning mechanism. And the load is 0 to 60 kg and the turning angle is 90 degrees. HanGrawler moves straight, turn right, and then move straight again. A motion capture was used to measure the movement. Regarding the result, HanGrawler realized 11 degree per sec turning movement, like this movie. HanGrawler enters the turntable, rotates the body, and exits the table. This graph represents the rotating angle. Thus, HanGrawler turns 90 degrees at angular velocity of 11 degree per sec with a load of 50 kg. It appears that turning movement was achieved at the target load 50 kg. When 60 kg load, the velocity decreased to 8.5 degrees per sec. So, we consider that the moment of inertia was influential on the turning speed. In summary, the main points of my presentation were here. Our future work is to develop an optimal route design method for production sites using this system. Thank you for your listening.